Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting topic where the idea is to predict the number of samples for in-context learning. This is based on the best paper at ECR 2025. So let's get started and see how can you predict the number of samples and why do you need to predict the number of samples. Okay. So standard in-context learning that is done with large language models, basically it depends on something called as few-shot in-context learning, where a fixed number K of samples examples is basically also supplied along with the original query so as to essentially get a reasonable classification decision, right? But the authors basically claim that, hey, dynamic K might be useful. It might not be a good idea to use static K, static number of samples, but a static number of examples, it might be good to actually have a dynamic number of examples. And that is because some examples may be easier to classify than others. So for more difficult to classify examples, maybe you use a larger K. For smaller ones, you can use a smaller K. For easier ones, you can use a smaller K, right? Also, the typical way of actually passing the static number of examples in a few short learning setup is to actually do a retrieval from a large pool of examples and find the k nearest neighbors and put them as exemplars, right? However, the quality of these k nearest neighbors may vary, and therefore it is useful to actually have a dynamic k. So therefore, this is the framework that the authors actually propose to have adaptive in-context learning, where the number of examples is varied per sample in the test set, right? So there is a training part to it, which is at the top, and there's a test part to it, which is at the bottom, right? So in the training part, essentially they train a multi-label classifier, right? Which basically can predict what should be the number of examples that you should use for this particular sample in the test in the data set, right? At test time, they actually make use of this train model so as to predict what should be the number of similar examples to retrieve. And then they obviously, prepend these examples along with the current test data point so as to ask the LLM for the right decision. Okay. They experiment with classification kind of problems only in this particular paper. Okay. So at train time, which is at the top, let's say that this is basically a sentiment analysis example or some such classification, text classification problem. So the input data is this, the input data sample is this. We never really feel involved with the story as all of its ideas remain just like that, just that abstract ideas, right? So what they do is to basically get top M similar examples, basically using sentence BERT retrieval. Okay. M in their paper, they fix M to 10. So they basically retrieve 10 different examples. And then they basically give those examples. So they give the first example, top 2 examples, top 3, top 4, up to top 10 examples. So to an LLM and get the output, get the label as predicted by the LLM. So therefore, they make like 10 different LLM calls in that senses. Okay. So this leads to basically 11 different predictions, zero with the 0 shot ICL, 1 shot, 2 shot, 3 shot, up to 10 shot, right? So that gives them a 11 sized vector. Now, the idea is that given this example, they have this 11 size label, which indicates whether the answer was correct or not. Okay. So this is basically the data set which is used to learn this multi-label classifier. Note that this is not a multi-class classifier, but more like a multi-label classifier. Now, it is also possible that with 3 exemplars, you got the right result from the LLM. Also, you got the right result from 7 exemplars and 8 exemplars. But with everything else, you basically got wrong results. Okay, so that is how this vector would look like. And they use this kind of a vector so as to train their multi-label classifier model. Okay. So now, obviously, you can train a multi-label classifier model. However, how do you use this model? Because when you want to use it at inference time, the model might say that, hey, making use of 5, 6, or 7 exemplars is a good idea. Now, which one would you choose? So therefore, at inference time, to choose the right number of exemplars, they propose 2 different heuristics. One is the smallest index with prediction equal to 1. So if the prediction was 1 for 5, 6, and 7, you would just go ahead and choose 5 exemplars, okay, because 5 is the smallest. Okay. And the other way is to basically choose the one with the highest confidence. So with every class label, a multi-label classifier also provides you the confidence or the probability associated with that class label of being 1, right? And therefore, if the probability was highest for, let's say, the number of exemplars equal to 6, you would just go ahead and choose that one. They observe that the highest confidence-based choice is actually better compared to the smallest index with prediction equal to 1. So how does their method perform? They evaluate their method on 4 different text classification datasets: sentence and analysis dataset, SST2, TREC question classification dataset, COLA grammatical error detection dataset, RT language inference dataset. So as you can observe, they are all binary classification tasks except for question classification task, which is basically a 6-class classification task, right? They come across various, these data sets come from different domains, and they also have variation in terms of the length of the input. So the language inference RTE dataset, textual entailment dataset, is basically 52.4 average number of words. Okay. So they experiment with 3 different kinds of models: Llama 2 7 billion, Phi 2, and Llama 2 13 billion models. They also experiment with 5 different methods. So zero shot basically means you don't give any few shot exemplars. FICL basically is fixed ICL. You basically, on a validation set, select how many exemplars you would use. And, for example, in this data set, you use 9, in this data set, again 9, in this data set 10, and in this data set 10. Okay, and then you use the same static number of exemplars across all test samples. AICL-E, which basically means that the multi-level classifier, obviously AICL means adaptive ICL, which is basically their paper. So in AICL-E, you basically just use embedding-based features. So you take the original text input and you embed it using SentencePert, and you provide that as features for the multi-level classifier to predict how many exemplars should be used for this sample. Okay. AICL-E plus N basically means that you supply more features, not just the embeddings of the text input, but also some more features denoted as N here. N is basically a M+1 sized, a M sized vector. Okay, so where M is basically the number of exemplars, max number of exemplars possible. So for any test sample, what you would do is to basically, retrieve M in the sense 10 different, 10 nearest neighbors from a large pool of exemplars using SentencePert similarity. And then for those exemplars, you try to figure out what is their label. Is the label, positive sentiment for all of them, or is it negative sentiment for all of them, or is it positive for 6 of them, but negative for the remaining 4, and so on. Okay. So the idea is that for each of those exemplars, for each of those 10 different exemplars that you retrieved, you essentially take their labels and pass that label vector as an extra input feature here. The idea is that if there is voting, if there is, if the top few nearest neighbors all agree on the label, then high probability that this is a simple to classify test sample, and therefore you can actually do with a smaller number of exemplars, right? So that is why they use both these feature sets: E, the embedding of the input, and N, the class labels of the M nearest neighbor exemplars. Okay. AICL star is a spatial AICL method where you exactly know how many exemplars to use. And then you just go ahead and use that and then compute the precision recall F1 for these different data sets using different models. Okay. So, AICL star is obviously not a practical method because practically nobody is going to tell you, magically how many exemplars make the best sense here, right? So obviously, therefore, these grayed out AICL star rows, you would observe that would, they provide you the best results, right? On the other hand, you also observe that the practical method AICL E plus N gives you significantly reasonable results, right? So essentially, you see precision recall F1. They are not too low compared to the ideal results. And obviously, they are actually much, much better than zero shot ICL or even fixed in context learning, right? Across data sets, across different models, showing basically the consistency with which this approach wins over zero shot ICL, zero shot in context learning, or fixed in context learning. Okay. Now, you see on the right side, what you see is 4 charts, each one for each data set. And what you observe is that Llama 2 and Phi 2 are being compared with a comparison between a fixed ICL and this adaptive ICL. So for adaptive ICL, obviously you use the same, you basically decide using this multi-level classifier what is the number of exemplars you should use or demonstrations you should use. Okay. While for fixed ICL, they vary the number of demonstrations and they keep that thing fixed for the entire data set, right? So essentially they choose 0 exemplars and then identify or check on the test set of SST2 what is the accuracy that you obtain, or macro averaged F1, right? Similarly, you can fix it to 6 for all the test samples and then observe the accuracy and so on. So the curve basically shows, at least for SST2, that yes, the larger number of examples, demonstrations that you take, the better results you get. However, you never get better results compared to the adaptive ICL. The best part about adaptive ICL is that you don't need to tune this hyperparameter, so to say, which is the number of exemplars that you should use, exemplars or demonstrations that you use in your ICL. While in fixed ICL, you have to first tune that, and second, you still get worse results compared to the adaptive ICL. Okay, and this kind of observation holds across all the 4 data sets. In fact, in some of these data sets, you also observe that sometimes using smaller number of examples or some smaller number of demonstrations is actually better than using large number of demonstrations. So therefore, a fixed number of demonstrations is a bad idea. First, it requires hyperparameter tuning, and second, it doesn't really give you as good results anyway. So in summary, in this video, I talked about adaptive ICL, which folks basically show is better than the standard ICL by up to 17%. They evaluated on 4 different data sets. The idea was to choose a variable number of demonstrations or exemplars in few short ICL depending on the current sample. The number of examples or the number of demonstrations to use is decided by a cheap multi-label classifier, which uses the embedding of the input text and the class labels of neighbors of neighbor demonstrations, right, as features. Okay, so on 4 different data sets, they basically show that adaptive ICL is better than zero-shot ICL or fixed ICL. That's it for this video. Thank you for watching. Hope you like the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.